In this video, we're going to be building off what we talked about in the last video with measurements, with a topic known as significant digits or significant figures, commonly referred to as sig figs. So the number of what we call significant digits in a value express the level of precision of that value. So we were talking about this in the measurement video, how it's important to record your data to the appropriate level of precision for the instrument that you're using. What we were really talking about there was sig figs. So they express the level of precision with which a measurement was made. A number or a piece of data that is expressed with fewer sig figs is considered to be less precise. So, for instance, if you report the mass of something as 1 gram, that means that that number could actually be anywhere from 0.50 grams all the way up to 1.49 grams. So that's a pretty big variance. That's the variance of an entire gram, half a gram in either direction, essentially. But if we instead report that as 1.00 grams, mathematically the same number, but it's very different to a scientist, this is now telling us that this could be anything from 0.9950 grams to 1.0049 grams. So that's a much tighter range. So by putting in those extra zeros, by putting in those extra significant digits, we're showing that the measurement was more precise, that there's a much lower variance in what that mass could actually be exactly, and that's why it's really important to express our measurements in science to the appropriate level of precision. So we do need to recognize that all measured values do have some amount of uncertainty. No matter how precise your measurement is, it's never really perfect if it's truly a measured value. So that means we must express them to an appropriate number of significant digits. So examples of measured values are all the things you would think of typically: length, mass, volume, temperature, time. The list goes on, but those are some common and familiar ones. But not all quantities are measured, and that's also important to recognize because we do treat those numbers differently. Some numbers are actually exact. Exact values have no uncertainty and are therefore treated as having infinite sig figs. Examples of exact values are anything that you can count, so any countable objects. If I have 6 pens on my desk, I have exactly 6 pens on my desk. There are no fractions of pens, that number is not uncertain at all. If I have 19 apples in my fridge, it is exactly 19 apples. So anything that you can count is considered an exact number. And the other one that you'll encounter a lot in this class is defined relationships between numbers, like unit conversions. A lot of unit conversions, not all of them are technically exact, but a lot of the familiar ones are. So something like 12 inches being equal to 1 foot, that is the definition of that unit conversion, and it is exact. There are exactly 12 inches in 1 foot. That there are 1,000 milligrams in a gram. That is a defined relationship. It is exact. There is no uncertainty in that number. So when we deal with these types of values, we treat them as having infinite significant digits. So the number of significant digits in our data is going to impact how we do calculations with that data. So it's important that we be able to identify how many significant digits are in a value that's presented to us. So there are some rules for counting sig figs. The first one is that any and all non-zero digits are always significant. So for example, if we have the number 376, the 3, the 7, and the 6 are all significant. So this number has 3 sig figs in it. So all non-zero digits are always significant. It's only zeros where things get a little bit weird sometimes. So there are essentially 3 different kinds of zeros we can have. Zeros between non-zero digits are the easy one. Those are also always significant. So for example, the number 4096, we have 3 non-zero digits, which are always significant, and then we have a 0 in between 2 non-zero digits, which is also significant. So this number would have 4 sig figs. Next up is what we call leading zeros, meaning zeros at the beginning of a number. Are never significant. So for example, the number 0.00208. We have the 2 and the 8. Our non-zero digits are definitely significant. The 0 in between the non-zero digits is also significant. But these 3 zeros in the beginning, those would be what we mean by leading zeros. They're the first digits in that number. So this one has 3 leading zeros in this example, and none of these are significant. Now, a note on numbers that are not significant. What we mean when we say that a digit is quote-unquote significant is that it is a meaningful part of the measurement or the measured quantity. It doesn't mean that it doesn't need to be there. So those zeros are still mathematically important, but they're not a meaningful part of the measurement. So you can't just take them out of the number. This is not the number 208. This is very, very different than the number 208. But from a measurement standpoint, we do not consider those a significant digit. So they do still need to be written as part of the number. They're just not counted as significant digits for calculations. So the last situation that we can face is what we call trailing zeros, which are at the end of a number. And these are the tricky ones because sometimes they are significant. They're significant only when there is a decimal point in the number. So let's look at a couple examples here. We'll do 1090, 1090 with a decimal point at the end, 1090.0, and then something a little bit different, 00960. So looking at these four examples, considering the rules that we've talked about, if you want to pause here and try these on your own, absolutely feel free. So non-zero digits are always significant. Those are the easy ones, easiest ones. Any zeros in between non-zero digits are always significant. So we've got those in the first three examples. Leading zeros we only see in the last one. Last example has 3 leading zeros. We know those are never going to be significant, so we can cross those friends out. And then we've got the trailing zeros in all of these numbers that we need to consider whether or not they're significant. The trailing zeros are kind of the only questionable case about whether they are or are not. And that is going to hinge on whether or not there is a decimal point in the number. So we see in the first example there is no decimal point, which means that this trailing zero is not significant. So this number here only has a total of 3 sig figs. The next example, there is a decimal point, which now makes that trailing zero significant. So just the presence or absence of that decimal point changes this number between 3 significant digits and 4 significant digits. And yes, that is absolutely a valid thing to do, to just put a decimal point at the end of a number with nothing after it. It's not commonly used in practice, but it is a thing that you can do. In the next example, we have trailing zeros both before and after the decimal point. Both of those are significant. If there is a decimal point anywhere in the number, your trailing zeros are considered significant. So this one, this version, would have 5 sig figs. And then again, in our last example, we have a decimal point anywhere in the number, so that trailing zero after the 6 is considered significant. So this one would have 3 sig figs. So we need to consider significant digits when we are performing calculations. So when we're performing calculations in science, if those calculations involve measured quantities, and if they don't, none of this applies, but if they do involve measured quantities, your result of your calculations must be expressed essentially to match the precision of your least precise measurement. And exactly how you do that depends on what type of function you're using. We're going to focus on just the basic 4: addition, subtraction, multiplication, and division for right now. So for adding or subtracting, your result of your calculations should have the same number of digits after the decimal place as the measured value with the fewest. So if you're adding and subtracting, the total number of sig figs actually doesn't matter. You're just looking at how many digits come after the decimal. So for instance, if we're doing 6.92 plus 7.4, our first number has 2 digits after the decimal. Our second number only has 1 digit after the decimal. So that means our final answer should only have 1 digit after the decimal. You always want to match whichever one is less. So when you do this in your calculator, it's going to give you 2 digits, but you need to round appropriately. So the appropriately rounded answer for this one would be 14.3. So your calculator is going to give you 14.32 here, but we know that we can only have 1 digit after the decimal and 2 rounds down, so 14.3 would be the correct way to report your response here. For multiplying and dividing, is when the total number of sig figs is what matters. Your result should match, should have the same number of significant digits as the measured quantity with the fewest significant digits. So if we wanted to do 520 times 0.145, 520 without a decimal point at the end only has 2 sig figs. 0.145 has 3 sig figs. Remember that leading zeros are not significant. We want our answer to match the value with the fewest number of significant digits. So rounded appropriately, the answer to that would be 75 to 2 significant digits. One other thing to keep in mind that we'll talk a lot more about later is that for multi-step calculations, you want to make sure that you're really rounding only at the end, not between every step. So we'll talk a lot more about that as we get into more calculations further down the line. But for now, just being able to do some basic calculations and rounding appropriately is good enough.